All right, recording started. It's Monday, March 7th. You guys have got a group set up, so hopefully you guys found a seat that you like. So we're doing a 2 name tag system. The top name tag, your name's already on it, this is for rows, but the bottom name tag, if you're happy with your seat, then go ahead and write your name in there and start doing some group projects. I've always liked doing a group project in the past, but COVID's been pretty bad the last couple of years, but checking the numbers and I think this thing's over, so pretty close. So yeah, we'll do some toothpick bridges and today. We've got top scientists for the last quiz you guys turned in, units 2 and 3. So if your name is up here, then awesome job. You guys are doing great. Look at all those names, all those top scientists. If you haven't turned that in yet, then pretty soon, because this week is last week of quarter 3, and we're going into spring break. Speaking of spring break and schedules, let's look at schedule we're looking at here. So this week we're going to be doing this group project, toothpick bridges. There's no school this Friday, so yeah, first day of spring break. When you guys come back, the next units we're going to review are units 4 and 5, so that's energy and momentum. Now I do have upcoming due dates. I have opened the next AP classrooms for those. So let's have those due dates as March 24 or March 31st. I think we cover a unit per week. Then that's a good pacing. Then I can fit in some other topics too that my other students are doing. So try to do that. Send some FRQs. Review each unit. So what are some of these other units that say my honor students are doing that like you guys know too? So coming back from spring break, I'll be covering thermodynamics and materials with and a little bit of engineering with my honor students, and do some of that stuff with you guys too. Engineering a toothpick bridge, that's materials and engineering. I know I've been telling you guys been doing electricity and direct current circuits with you guys, so they've rearranged the schedule, so we'll do that probably in about April, and then of course we have to review these other topics too. So I'll put a few other topics in there too, but this is some of the schedule we'll be looking at. Let's see. All right. I've got a show and tell piece for you guys. You guys remember back on Friday, I was reading you guys some stuff about concrete. We were talking about concrete grading. We're talking about a sieve that you use to see what's the distribution of different particle sizes you have for concrete. We were talking about steel reinforced concrete. How can you measure the strength of concrete, like compressive strength, right, which might be like 20 to 30 megapascals? We've got like 200 or 300 atmospheres. So this is the leftover remains of a cylinder that was 4 inches in diameter, and it used to be 8 inches tall. That's back in my university days. Put this in a compressor and smash until it breaks. It's going to pull a stress strain curve. Let me show you guys. I know you guys probably see some new posters hanging from the ceiling. I'll show you guys a few of them that are probably more after spring breaks. But some engineering terms, stress and strain. So stress is, well, it's pressure but applied to solids. So it's force per unit area, like this force per this cross-sectional area. Now, this picture down here, I'm showing it in tension, but you could go compression and be the same idea. So it could be either way. And then the resulting strain, well, that's percent elongation. So if it elongates by like 1% or 2%, so it's delta L over L naught. Okay? And a lot of materials will have this stress strain curve. Some of you guys are probably going to go into engineering in college. You'll see the stress strain curve all over the place. Now, this particular, we're looking at the ratio of stress to strain, that's the slope of this line right here, is called Young's modulus. That's a material property. So there's a Young's modulus for steel, there's a Young's modulus for concrete, there's a Young's modulus for copper. Right? So different materials will have different ratios of stress to strain, right? Force per area to percent elongation. Now, anything that's actually on this line is in the elastic zone. So if it stretches or compresses a little bit, it'll just bounce back to normal once you take the stress off. But anything beyond this point, it goes into permanent deformation. So just like you take a paper clip and maybe clip a couple of papers together, and then take the clip off and just go back. But if you twist the heck out of it, it'll be permanently deformed until it eventually ruptures. Now, concrete, the whole thing looks about like that. It just snaps. But metals like steel, well, they might have like this whole extra additional part of the part there. I did tell you guys about this back on Friday, coefficient of thermal expansion, also material property. So how much does something expand for increased temperature? Well, it depends on the material, but steel and concrete have almost the exact same coefficient of thermal expansion. There's actually a small window with an overlap. That's why you can create good reinforced concrete. Why not? I got this one up here. So I know I've got a lot of those too. Did I do scaling with you guys probably sometime in the past? I think so, right? So if you scale something by some linear factor, I threw lambda here, why not? So let's say a factor of 3. What else changes? Well, the surface area would change by factor of 9. Anything to do with volume would change by a factor of 27. So it's linear factor to the power of 2, linear factor to the power of 3. Something like that. Okay. All right, let's take a look at toothpick bridge quest. So your guys' assignment is to build a bridge out of toothpicks to span a 20-centimeter gap. Okay. Now guys, 20-centimeter gap, does that mean you want your toothpick bridge to be 20 centimeters long? No. Do you want it to be 18 centimeters long? Yeah. Then it would become a raft. How about 25 centimeters? That would be okay, right? You want it to be more than 20 centimeters, right? Because I'm just saying it because I know from the past, a lot of groups they build to 20. Right. Then what we'll do is I take this 8-centimeter diameter ring. That's this right here. This is this. Right? I'll put this on top, then put the gray thread on top of that, and then start putting in lab weights. We're gonna see who's can hold the most lab weight. So this is gonna be a few days project. Of course, if it's just toothpicks and Elmer's glue, there's going to be a lot of patience with the glue drying. It's going to have to be over several days. You might want to today with your teammates come up with a design and then start gluing the panels together, right? And to actually put those panels together over the next few days. So your budget is 100 toothpicks and Elmer's glue. So here in about a couple minutes, I'll give guys 100 toothpicks per group. So I think I hit all the points I have to hit. You guys got any questions? All right, well, let me get you guys your toothpicks, and you guys will use your imaginations and do some engineering.